we've been talking about ideal reactor types. We had perfect mixing, we had perfect plug flow, we had perfect batch reactor behavior. And each of these reactor types don't really occur in nature. Even the batch reactor, which is more achievable, we can certainly stop flow into and out of the space. But there also we rely on the system being perfectly mixed. In this section, we are going to introduce the residence time distribution concept, and we'll see how we can use it to examine cases and model reactors that do not exhibit perfect mixing or perfect not mixing behavior. We have been talking about our reactor systems in terms of them being perfectly mixed, both in terms of the material and energy distribution. Now let's talk about a more real-world case. So in a real reactor, our flow patterns may be complicated like this. So in this diagram, we have the arrows showing us the direction of flow. So our system might not be flowing in one direction, or it might not be perfectly mixed, which would show up as turbulence. It might have flow features in it which reveal different types of zones in the reactor. And that's in terms of the flow. That may also be true in terms of the concentration and temperature fields. So you might have low temperature regions and high temperature regions, or low concentration regions and high concentration regions. So we can imagine near the inlet point, there might be a high concentration of reactant and so on. So in real reactors, all these things happen, and we then are concerned that the models we've been developing no longer apply, that they are based on such restrictive assumptions that they will hardly ever reflect reality accurately. And if that is a concern, that is a serious that may be a serious issue in terms of our ability to predict what that reactor will do. So up to now, we've been estimating the reactor volume or developing an energy balance based on the idea that we can estimate a reaction rate for the reactor. So we happily wrote minus RA equals KC something. Now, if we look at a picture like this, we can see different temperatures, different concentrations. So we will have different reaction rates at different points in this reactor. Also, in terms of the flow, we don't know how to handle this situation where the system is not fully turbulent and hence perfectly mixed, and it's not flowing in regular straight lines. So if we have some other strange types of mixing pattern, then we are not clear about how we can model this. We don't know how to account for flow into or out of a region. And as we'll show now, the residence time distribution helps us do that quite efficiently. And RTD, as we often call it, is not a new concept. It has been applied very effectively in chemical engineering, but RTD, or residence time distribution, is the same as an age distribution. So when we say residence time, how long has something resided? How long has something resided in a specific space? And in fact, we have dealt to some extent with some variables of this nature. We introduced the space-time, and we made some suggestions about why we thought the space-time had to do with the average time spent in the reactor. And if you think about some of the reactor comments that we made, we often talked around the concept that the more time we spent in the reactor, the greater the extent of the reaction. So we can see that time spent in the reactor space is key to our ability to predict what it's going to do. And in fact, when we start looking at some of these lines, we can imagine that there will exist zones where the fluid flows through pretty quickly, and so it spends a short amount of time, let's say, along this stream. There are other regions where the fluid might circulate in some kind of pattern, and the fluid that happens to go through that region will spend more time on average, so it will be reacted to a greater extent. So we can start to think about the complex interplay between flow, right, our flow stream, so our velocity vector fields that represent the flow pattern. So the flow pattern is related to the duration that the fluid is going to spend there. So as we said, this fluid might spend more time just because we can see there's a possibility of circulating in here for a while, whereas fluid that flows around here, that has a different flow pattern, and this will likely spend less time than the fluid here. So there is a relationship between our flow pattern and the time spent reacting in the space. So we would like to avoid this level of complexity. Right, so computational fluid dynamics is a well-developed field, and you can generate pictures like this, but we would like to think about a more elegant way of doing this. So we can brute force go and divide up our reactor into tiny little differential elements, stack them next to each other in some kind of discretization grid, and solve our material, momentum, and energy balances like has been done here. And that requires significant computational resource. And we want to show now that the residence time distribution affords us a much simpler and more elegant alternative. And in this picture, we are just showing again that kind of understanding that, let's say we have some real reactor and there exists some zone near the middle that flows something like a plug flow reactor. And we can see here that the stream is pretty quick. And so we'll have a short duration for the fluid flowing through here. And then there may be regions, something like in the corners of the reactor, where fluid is circulating. So it's circulating, but it's not exchanging material so easily with the rest of the fluid. So the fluid in here is going to spend on average more time. And then you have regions out here which are better mixed. So you can see, you can imagine better mixing patterns near the wall here. So it might be that if you have a fluid with significant viscosity, that due to wall drag here and the tendency for a high flow near the middle, that the difference in those velocities cause some kind of turbulence in this region. So we can imagine that there are something like 3 different types of zones here. And we can then start to think about forming a network of models. So we can say, if I consider the fluid near the middle here, this looks to me something like plug flow behavior. And then if I look here, where the fluid circulates in its own space for some time, that's something like a batch reactor. And then the fluid here, which is turbulent and well mixed, that's something like a CSTR. So that introduces the notion of compartments and being able to take a real reactor and identifying zones that are more similar to the reactor types that we are familiar with. So we can imagine that if we could break down some real reactor into a network of simpler, more ideal type reactors, that we'd have some hope of modeling this reactor. And that's in part what we do. So later on in this section, we will come to the compartment models, and that's pretty much what we do. And there we try to answer the question, how much volume is dedicated to plug flow behavior, how much to batch-like behavior, and so on. So that's the motivation for undertaking the study of residence time or age distributions. And like we said, age distributions are not really a new concept. So in chemical engineering, we've borrowed this concept quite effectively, and we use it. It's part of our classical theory now. And in a way, using the term residence time distribution is our way of laying claim to this field. But actually, it's the study of age distributions has been around a long time. And you can easily imagine that in terms of countries and keeping an accounting of the people in countries and the characteristics of the populations in countries, there have been many, many attempts to determine the age distributions. And in fact, these are things that influence our geopolitics. So if you think about, you may have heard about the concerns, the growing concerns in Japan with an aging population, about the number of people available to undertake the work required. You may have heard about countries with younger population looking to step into a role that would improve their economies and so on. So age distribution has been an important topic for a very long time. And if you think about our planet, there exists an age distribution in our planet. We'd be able to say that the number of people less than 2 years old, right, the number of babies and toddlers, there's a certain fraction of the total population in that age range. So in this population of currently around 7 billion, there's a certain fraction that are less than 2 years old. There's a certain other fraction that are more than 2 years old but less than 10 years old. There's a certain other fraction that's more than 90 years old, and so on. So we can imagine that there exists an age distribution in the planet Earth. And of course, then we can also talk about an age distribution in a particular country. So the age distributions may be different from place to place. So one country's average age may be greater than another country's average age due to differences in nutrition and other factors like that. So there exists an age distribution in a space. And in a similar way, a reactor has the same influence. So in our chemical reactors, we can identify fluid elements, so packets of fluid that have been in the reactor for a greater period of time and packets that have been there for a reduced period of time. And that is important in particular to us in predicting the reactor's performance. Because if we know that there's a large number of fluid elements that have been there a very long time, then it might be that they have a low reactant concentration and it's harder to get a good rate out of them and so on. So those are the things we are concerned with. You might be intrigued by these comments. So I used to say these things that there's a certain birth rate into the planet, and we can speculate about where those people come from. And then there's a certain exit flow from the Earth also. So there's a death rate that we can identify. And we can also speculate about where those people go as well, and what it is that's going, if anything is going anywhere. So I speak much more conservatively these days. When I was young and idealistic, I used to make all kinds of comments about a recycle flow. So you could model reincarnation with a recycle flow and so on. So you can avoid all those centuries of religious conflict. So I used to say things like that. Well, I guess I'm still saying them, but just kind of pretending I'm not saying them by just referring to my earlier self. But anyway, you can see here the connection between the mathematical view of age distributions, where we often talk about birth and death rates, and we can look at the chemical engineering version of that, which is an entrance flow or an exit flow. And it is important to think about this because if you consider a high birth rate, if you have a country with a high birth rate, then you can imagine that there will be a relatively high proportion of young people in that population. And in a similar way, if we compare a reactor with a high entry flow rate, then we will have on average fluid elements that have a lower residence time. So there'll be fluid elements that have spent less time in the reactor. So it is important to connect with the age theory because in a way ourselves as human beings find these things easier to understand. So it's a convenient crutch for us to understand the age distribution theory. And of course we've been talking about the space-time. So if we take the volume and divide it by the volumetric flow rate, then we know we get the average time spent here. So if we consider the average life, the average lifespan of a person on Earth, then if you look at the total death rate and divide that by the total number of people, so I'm not sure what the total death rate is, but it's going to be some number that looks like this. So I'm not sure about my numbers here, but let's say the average age is about, maybe 70 these days, so 70 years. And that's equal to our total number divided by our flow rate. So our total number is about 7 billion. So 7 times 10 to the power 9, and then divide by Q. Divide by Q. So you could say from this that our average death rate is 7 billion divided by 80 years. So that's the average death rate. And of course, that's under the simplifying assumption that your death rate equals your birth rate, which we know is not completely true. But anyway, that starts to give you some sense of how you can quite quickly and easily start understanding some of the quantities involved here. Okay, so that introduces the topic. And now let's start introducing some of the basic variables we'll be using. So we define theta to be our age variable. And of course, our age is equal to the current time minus our entry time. So we entered the planet at a certain time, at a certain real time. And we typically call that our birth date. So if you take the current date minus your birth date, that hopefully gives you your age, right? And if I refer to my younger self, I would often at this point make a joke about as long as you are not moving close to the speed of light, then your age is simply that kind of relationship, right? But anyway, we all know our age is the current date minus our birth date, and the same applies to any packet of fluid elements. So the current age of a fluid element, the residence time of a fluid element, is equal to the current time minus the entry time. So let's just switch on over to make a sketch here. So let's imagine in our reactor system, we have some reaction space of interest, and we are feeding it with a stream here and withdrawing here. And of course, we understand this to be a continuous stream of fluid. And we can imagine different packets of fluid here. So in our pipeline, we can arbitrarily segment the fluid elements like so. And we are doing this because we can see that these will each enter at different times. So this one will enter the reactor at time T10. And then that will enter, and after some short time, the next one will enter T20, and then after that, the next one will enter T30, and so on. So eventually, we will have fluid elements from those three groups in the reactor. And of course, these groupings are by no means any kind of real thing that you can see. This is our imaginary little box, and of course within each box there are molecules freely moving around in here. And it might be that in this thin pipeline that they were relatively separated, but once they are in here they are free to move around, so those molecules are moving around in here. But of course each of those molecules has come from a particular fluid element. So if you pick any molecule and you ask it, hey, when did you get in here? And it would be able to tell you, well, I only got here at time TOI, whatever that is. So we can identify for all the fluid elements in the reactor that each molecule in there, in fact, has entered at a specific point in time. Sorry, I should say a specific instant in time. Right, so we can talk about points in space and instants in time. So that exists. So a birth date into this space exists. And of course, this definition is entirely arbitrary. We can define our age in any space. So when we refer to our birth date, we are referring, there are many implied assumptions there. It's referring to the Earth in general, all countries on the Earth as being our birth date. In fact, it's really about our existence. Well, anyway, let's not get too metaphysical. We can define our time of entry to a space in this way. So we have defined TOI as the time of entry, but at any instant in time, right, T, we can take a snapshot of this whole space. So we could say, well, I want to know currently at this time T, I want to know what's the distribution in the space. So for this given time T, we can count up certain numbers of fluid elements that entered at these different times. So if we are looking at this reactor at some time T, we can identify that there are certain fluid elements that have spent a certain age there, right? Remember, we defined theta to be age. So there exists a certain fraction of fluid elements of one age, of another age, and so on. So there exists a distribution with respect to age inside this reactor. And this distribution relates to the fraction of fluid elements, or the proportion among fluid elements, having entered at different times in the past. So when we wrote theta equals T minus T naught, right, this applies to some specific element. So I, right, our age is personal to us, right, as personal as our birth date. So when we look in the reactor at some given time T, then we are saying all these fluid elements are currently in the reactor at time T. So T exists for all these fluid elements. So if you ask any member in this reactor, what's the current time? That member will say the current time is T. But specifically to that element, if you go on to ask, well, when did you get here? Then it would say, well, I got here at this time. So there exists an age for each of these fluid elements. So when we segmented this, if we take these as approximately small enough, then all these fluid elements we would consider as being at the same entry time, and hence they will always have the same age. So if you can find them, if you can find in the reactor molecules from this group, that group, no matter where they are, because they may have separated the molecule, one molecule may be sitting here, another one may be sitting there, and so on, they will each have the same age. So we can represent it like this. We can draw aging lines. So we can consider a specific group of fluid elements. So let's say we look at this one. So this group has entered at this time. So this is the T naught value for this group. And then as time progresses, that group is of course getting older. And of course it's getting older at the rate of 1 second per second. So every second that passes, it gets older by 1 second. Right? And then you can insert your favorite joke about as long as you're not moving close to the speed of light and so on. Okay? So you are getting older if you look at a specific group, and then of course all groups are aging in the same way. So if you pick another group that entered sometime later, it will also be getting older in the same way. And then if you pick any other group that also entered, then that's also getting older at some rate. Well, at the same rate. And then you could take a slice through this and say, well, I am currently interested in this specific time in the reactor, this value T. So you would be slicing vertically like this. So you can say, well, from this group, how many of you are left here? From this group, how many do we have now? So maybe 20 entered, but maybe by the time we are looking at the reactor at time T, only 15 are left over. So the amounts change over time, but we can keep an accounting of them in this way. Through these aging lines, we can say, well, if you guys are this age, then I know you entered back at this time. Right, so this is a set of aging lines, which it's quite convenient for us, especially if you are interested in solving the characteristic equation and things like that. But anyway, it's just representing that our age is nothing but the current real time minus the birth date. Okay, so that's introduced those basic definitions, but we've also started talking about the proportions of things. We said when we look vertically through the space, that there exist different proportions of fluid elements, different amounts that entered at this time, different amounts that entered at that time, and so on. And so there exists a distribution of age here, right? And we also introduced that here. We said that if we look at the reactor at time t, there will be fluid elements of different ages here. And now we want to introduce this, this I more formally, and we are going to define I. So define it such that if we go and multiply I of theta by delta theta, then we will get the fraction of fluid elements that's currently in the reactor in age range theta to theta plus delta theta. Right, so I of theta delta theta is the fraction in the reactor in the age range theta to theta plus delta theta. And that's typically how we define any distribution function. We create a function, right? In this case, it's I of theta, and we use the function to obtain fractions in specific ranges. And the reason we do it in this kind of roundabout way is because it's very difficult for us to talk about a specific age. So for example, if we take a human population, if you ask someone, or if you, well, let's say you ask someone their age and they tell you, I'm 20 years old. Now there's implied in that an age range, right? If you say you are 20 years old, you don't mean that in that instant when you were making that reply that you were exactly 20 years old, right? Instead, when you say I'm 20 years old, what you typically mean is I'm 20 years old during the course of this year, right? Between the start of this year and the end of this year, my birthday fell within that period. So when you give your age, what you mean is that your age is somewhere in this range. It's somewhere over this span of 1 year. Now we do that because it's pointless information to say I am exactly now 20 years, 6 months, and 5 seconds old, right? And that's because by the time we said that, already it's not true, right? Time has moved on. So we don't want to be so specific about the time. We want to identify fractions over age ranges. Another way to look at it is if we are too specific about this, if we are too narrow, if we are saying that our age is only in 1/1,000,000th of a second, then we will have a very small fraction, right? So that's why we define our distribution functions in terms of ranges. A similar thing with height, right? You can also define a height distribution. So let's say we want to know what proportion of the population has a height of, say, 5.5, or let's say 1.7 meters. So when we say 1.7 meters, we typically mean a specific range. We typically mean 1.65 to 1.75, right? That's what we mean, because there's likely a very small, there's likely a zero probability that anyone is exactly 1.7 meters tall. And in fact, it comes down to how accurately can you measure this anyway. So we we have to talk about ranges of things. So we can define a distribution function which purports to be able to report at as small an interval as we want. But typically, from the measurements available, we will be providing data in certain ranges, and we will be able to use that to then estimate the function. So anyway, that's the internal age distribution I of theta. That's the age distribution at the inlet point. Another age distribution we can introduce is that at the exit point. So we can define at the exit point E of theta. And it's the same definition as here, except that for E, it's the distribution at the exit point from the reactor. So you could be sitting out here and asking each molecule that comes through, so how long did you spend in here? So what, only 20 days? That's not much time for reaction. And then the next one comes along, how long did you spend in here? What, only 5 seconds? So you can identify the certain, you can identify out here the proportion of molecules that have spent specific time ranges in the reactor and are now at the exit point. So E of theta and I of theta, the internal and exit age distributions inside and from the reactor. Right, so I and E. Now we would like to know, how on earth do we measure these age distributions? Right, if you think about this situation, let's say this was simply water that was flowing through. Right, and if you look at this as a tank here, it's just a tank of water. You see no chemical difference between any one molecule and any other molecule. There's just no way to look at the molecules and say, oh, this one has spent so much time in comparison with that one. And that's a little bit at odds with the human populations. So in a human population, you can try and guess someone's age. So if it was a human, if we go back to our world reactor, right? If you were here and you met someone and you looked at them and you said, oh, I guess you are about 35 years old or something like that, you could do that, because implicitly we understand that people, they are born and then they are slowly rotting to death. And so you can observe the signs of that, and you can say, well, I estimate you to be about this age. So you can do that with another person. But in something as simple as a molecule, and let's assume now we are not looking at decay rates of subatomic particles and so on, that we are just looking at a molecule. There's no observable, there's no way for us to estimate the age of this molecule. And so we don't try to do that. An alternative is to say, well, what if we put a tag on some of these fluid elements? So let's say we tagged this group of fluid elements somehow, right? So if we put a tag on all these molecules, then if we observe the molecules here, and then you said, oh, I see, now we have 3 of these in this reactor, and I know from the molar mass that this amounts to a 2% proportion. So if I know the mass of all the molecules in the reactor and I know the mass of molecules of this measurable type, then I can say what proportion of the mass in the reactor is of this type. So that's one thing we can do. We can somehow tag the molecules in here. And an easy way to tag molecules is actually not to tag the molecules themselves, but to introduce other markers to that same fluid element. And we do it similar to the way I've drawn it here. We actually inject something together with that group. So if this is water and if we inject, let's say, a salt solution there, then we know that that salt is mixed with that specific group, And so if we can estimate the proportion of salt that we see in the reactor in comparison with the amount that we put into the reactor, then that's an indication of the fraction that also entered here. So just to say that a little differently, if we know that we've put in originally, let's say we put in let's say we put in 20 moles of that salt. Let's use a different. So let's say we put in about 20 molecules of salt, and we did this at some time t0. So at time t0, we injected 20 molecules of salt in. And then let's say we looked at the reactor at time t0 plus 10. So maybe it's 10 hours, right? And if we look at that reactor and if we measure the amount of salt in there, somehow we are able to measure it. And let's say we measure it and we find that there's just 5 molecules of salt left over. Right, then we'd be able to say that after 10 hours, that our fluid elements will be down to a quarter, right? 5 over 20, so 0.25. And we could do this as many times as we want. We could ask after 15 hours. So maybe after 15 hours we are down to just 2 molecules. Right, so 15 hours, it's 2 over 20, so it's 0.1. And then we could have done it earlier as well. We could have done it at 5 hours. So maybe at 5 hours it was more like 0.7 and so on. So you see here, this number is then the age, right? We are asking about what happened 10 hours after T0. So the age of those salt molecules is 10 hours. And similarly, we can ask about the age, or rather we can ask about salt off age 15 hours. We figure out that there's 10% left and so on. So in this way, we can create for ourselves a distribution. We can work out what proportion of our fluid elements are surviving to these different ages. And we can see in this case, because of the flow dynamics here, our salt is running out, and after 20 hours, there's very little left of it. And the assumption that we are applying here is that that salt mixes well enough with the water that the salt concentrations are a good indication of the water concentrations. So once more, if that salt is what we call a good tracer, right? If the salt is behaving in the same way, if it has the same flow pattern as the water in here, then that salt is a good indicator of how the water is distributing itself in the space. So the salt seems to be spending time that looks like this in that reactor. And we are then making the assumption that that salt is an indicator of the proportion of ages of the water in that reactor as well. So that's how that's one way of estimating our age distribution. You introduce something chemically different into your feed stream, and then you measure that chemical, and from that measurement, from measurements of this type, you construct an age distribution. And then you interpret that age distribution of that indicator, of that tracer, as being identical to the age distribution of the fluid that you are actually interested in. In this case, it's the water age distribution. So we can't measure the water directly, right? There's no chemical difference in the water. But injecting salt is chemically different because we don't have any other salt in the system. It was only pure water. Now that we have something chemically different, we estimate its age distribution and therefrom infer the water's age distribution. Right, so here there are little bits where I haven't directly connected these numbers to what does it mean in terms of age distribution and so on. So we'll do all this more precisely now, but this is in broad concept how we are doing this. Okay, so that's the concept of a tracer, and then again the tracer must be a good indicator. It must mix well, it must have the same hydrodynamics of as our fluid, and then we'll be able to estimate the age distributions. And here, this is just a comment. We will meet the Dirac delta function in more detail later. This is just a quick comment that ideally we would just pulse that tracer. So there are different ways to introduce the tracer. So the one that we just described now was a pulse tracer. So we introduce all the tracer in one quick shot. And in fact, rigorously speaking, or if you were to represent that mathematically, the Dirac delta function is an instantaneous loading of all the salt into that stream, and you no longer have salt after that, and you didn't have salt before that, so it was just in one instant that you introduced all that salt. So that's the pulse tracer. And we'll come back to these diagrams later. But for now, let's think about writing a mass balance on this. So we have this concept of a tracer, but and we can even imagine being able to get numbers like this out. But now let's try to convert that into a distribution function. And the best way to do that, of course, is just to establish for ourselves the mass balance around this. So let's create, let's say we are doing this in this reactor. And so we have our flow. So there's some, there's a stream through this reactor whose age we are actually interested in. And then we go ahead and we pulse some tracer in at a time that we define to be T0. And so this tracer is going to distribute itself. So after T0, it's going to be distributed in this reactor in some way. And then we are going to start to see tracer appearing at the exit here. And so if you observe at the exit point, right, so let's say T0 is here. So at the exit point, you won't have seen any tracer, right, because tracer only entered at T0. Then after T0, you might start seeing tracer appearing at some point, and then it will have washed out of the system. So here we are writing the concentration of tracer. Concentration of tracer, and this is time. Right, so here now I'm talking about some point at the exit. Right, so earlier we talked about measuring the concentration of tracer somehow inside the reactor, and we can't really do that, right? We can imagine it's very difficult for us to take samples all over this reactor to estimate the concentration there. So more realistically, we can look at the exit point and we can measure concentration, a salt concentration, as it's varying with time. Right, so we can accept that, yes, we pulse some tracer in here, and then we can observe out here, we can keep taking out samples and measuring the concentration of salt in this stream here. So there's nothing wrong with doing that. This is something that's practical and doable in any reactor. Okay, so we have a concentration of tracer, and now let's think about the mass balance that we can write for that. So first off, we can say that, well, there is a certain amount of tracer that that has entered in the first place, but if we just think about at the exit point at some time t, right? So let's pick just some random time t. So there's some time t, and let's also pick an interval delta theta. So we are going to take some interval here, delta theta. So T, so between T and T plus delta theta. So for example, let's say T naught was 1 o'clock, so 1300 hours. And then let's say our time T, let's say that was 5 minutes past 1 o'clock. And let's say delta T was 20 seconds. So we are interested in tracer that has exited from that reactor between 13:05 and I guess 00 and 13:05:20. Right, so in terms of real time, those are the times of interest to us. Now, we can also define for ourselves the volumetric flow rate. So let's say it was a steady state system. So you've got the same volumetric flow rate in and out. And of course, we have measured the concentration, right? The whole point of doing this was that we measured the concentration. And yes, we are talking about some small time range. So let's say it looks like that. So we are, it is some small time range, and so there exists some concentration during this time. So let's just call that C of tracer, and this was at time, what did we call it, T. Right, so that's the concentration of tracer at the exit point at time T. Now we could estimate for ourselves the number of moles of tracer that exited there. So we can say delta N is the number of moles of tracer that exited during that time period. And we can simply estimate that as Q, so volumetric flow rate times the concentration times the time period of interest, which is delta theta. Right, so 20 seconds has passed here, right? Delta theta is 20 seconds. And our volumetric flow rate is Q, and the concentration is CT. So this, if you multiply this together, is the molar flow rate of tracer at time T. And if you multiply that by delta theta, then that's the number of moles of tracer between the times T and T plus delta theta. Right, that's the amount that left during that time. So that's the contribution from that specific time range. Now, you can then say, well, if I go and sit here for an infinite period of time, I will eventually watch all the tracer leaving that system. Right, so you can say the total amount of tracer that I put into the system in the first place, that must equal the sum of all the tracer that comes out here. So the total amount that will eventually exit is the sum over all those time periods. So delta, I'm just leaving it, delta Ni, and that's going to equal the sum of all these things. So it's the sum. Now Q we are assuming is going to be constant. CT we know is changing. CT, and this is at Ti. So the concentration of tracer for the ith interval, and then delta theta. Let's assume we are taking the same delta theta all the time. Right, so this is the total amount of tracer that that was originally in the system, and now this is the amount of tracer that's left over in the system. Let's just clear up here a bit. And then we can say here that the fraction of tracer, so the fraction at the exit between T and T plus delta theta, is obviously going to be delta N over N. And if you compare these two, you can see there's a common Q here, right? Q is a constant of summation here. So there's a common Q which can cancel. and there's a common delta theta as well. Right, and so you're going to get here CT at TI over summation CT TI and I'm just going to leave the delta theta in here, right? Let's not cancel the delta theta. Okay, so the only thing we canceled here eventually was that Q, okay, which is fine. So we agree that's the fraction at the exit point in this range. So now instead of a number of moles, we have a fraction of our tracer that exited. Now if we think about this fraction at the exit, right, remember we had defined the function e of theta such that e of theta delta theta is the fraction of the fluid in that age range, right? So go back and just check you agree. E of theta delta theta is the fraction. So that was our definition of the distribution function. So that's fine. Now we can cancel this way. So let's cancel this delta theta with this delta theta. And if you look at the denominator here, you can identify this is nothing but a Riemann integral. In other words, you can write here E of theta is equal to CT Ti over the integral of CT. And that's quite an amazing result. It tells us that if we want to know the exit age distribution from that reactor, all we need to do is pulse in some tracer and then measure the concentration of tracer at the exit, and then just divide that concentration by the area under that concentration profile. So if we think about mathematically what this is, right? So we've been measuring the concentration of tracer here. Then of course we can measure an area under this concentration curve. And so that's some fixed number, right? Maybe we get 10 here, right? And then we just take the whole function, the measured function CT, and divide it by that integral. And that is E of theta. So that is all we need to do if we want to estimate E of theta for any reactor. And if you think of it, we made no prescription on the nature of the mixing here. We didn't say that it had to be perfectly mixed for any of this to hold. Right? If you go back and think about all these steps here, these are all simple definitions. We didn't need CSTR or PFR or batch reactor here. All we did was apply some basic Q times C and so on, with no assumptions behind those. And so this is generally true, right? This will work no matter what type of mixing we have in the reactor. So this is how we can estimate the exit age distribution from the reactor. So that's an intensely practical thing that we can do. We can get the exit age distribution in this simple way. Now this was not exactly what we were talking about, right? When we were talking about this reactor, we were talking about what proportion was in the reactor rather than at the exit point. So the other missing piece is the relationship between E of theta and I of theta, the internal age distribution. So we have now a nice way to estimate the exit age distribution. Can we now figure out what the internal age distribution was? So to do that, I'm just skipping here. The first thing we are going to do is introduce this new definition. F of theta is the integral from naught to theta E of theta. So remember, E of theta is the exit age distribution. So if we go and integrate from naught to theta, this is going to be the fraction of fluid elements that exit after age theta. So that's the fraction of fluid elements that spend at most theta in the reactor, or having exited the reactor. So this is the fraction of fluid elements up to a certain age that we observe at the exit. Right? Now, the maximum possible age is infinity. Right? Your lowest possible age is 0. You can't have a negative age. But in a reactor, we can imagine we are aging to an infinite period. We could have a reaction space where things have been sitting there forever. Right? So it's not like a human population where we say, oh, the maximum age is something. And in fact, we don't know that there is some maximum age. It's changing all the time. But anyway, in a chemical reactor, we can certainly more generally say the maximum, there's no maximum. So we'll just go to infinity. So let's just leave it open and say, let's consider all ages onto infinity. And then we could say the fraction of fluid elements at the exit point of ages at least theta can be represented this way, right? The fraction of ages at least theta. So all fluid elements greater than or equal to the age of theta, that is obtained by integrating E of theta in this way, from theta to infinity. Right now, clearly, that is simply 1 minus this. Right, so the total fraction is, of course, 1. If you add up all fluid elements, then the total fraction is a 1, right, just by definition of fractions. So the integral from, maybe let's write it like this. We can say the integral from naught to infinity of E is equal to the integral from naught to theta plus the integral from theta to infinity. Right, so we are going from naught to infinity, and we could simply interrupt this integration. We could, instead of going all straight from naught to infinity, we can go naught to theta and then theta to infinity, right? We know that's valid. Now, if we are integrating all possible fractions, right, that's another way to read this, right? All possible ages are naught to infinity. So if we add up all possible fractions, then that must simply be a 1. Right, so 1 equals that. So then we could say naught to theta equals, and I'm just going to copy it like this. So naught to theta or naught to infinity or theta to infinity is 1 minus naught to theta. Right, which is the same as 1 minus f of theta. Right, so that's what that means. So if you want the fraction of fluid elements of age at least theta, then that's what you have. So anyway, that's all rather formal. Let's again think about a material balance around this. So having established that, let's think about a fluid elements in some vessel. Let's just clean up here a bit. So let's think about a space where we've introduced our fluid elements into the reactor, but the system kept flowing, and we are now interested in some instant in time t. We've fed everything in at time t naught, and so over time we have been observing that our fluid elements have been leaving. So we spiked everything in at some time t naught, then they distributed in here, and then between t naught and t, our fluid elements have been escaping the system. And so we would like to have an accounting of the amount of tracer left over in that reactor. And we can talk about the volume of the space and I of theta. So we know the fraction left over in the reactor is I of theta delta theta, right? By definition of that distribution function. This is the fraction of fluid elements in age theta to theta plus delta theta in the reactor, right? So if we multiply that by V, then that's the total volume of fluid elements of that age range in the reactor. That must equal the number of fluid elements that of this age range that entered in the first place. And if you think of it, the amount that entered in the first place was Q, and the time range is delta theta. So if you like, this is the total amount of fluid elements that that entered the reactor in the first place that could possibly be sitting in this age range now, right? So this age range has a width of delta theta. So there's a certain period of time that passed delta. This thing looks kind of like a face, eh? So anyway, delta theta, that's what's passed, and now this is the amount that entered in the first place, and then the amount of this that exited, that must be the amount that's at the exit point. Right, that's going to be the contribution of all ages earlier than current time, than age of interest theta. So the integral of all those ages, so naught to theta, so that's going to be the fraction that was exiting during that time. Right, so here I'm going to write this as in terms of flow, right? E of theta, if you integrate this is the fraction that left the reactor, so up to time, up to age theta. Remember, now we are only interested in age theta here, and only between theta and theta plus delta theta. We only want to know how much is left over in the reactor of that age range. So we are trying to estimate how much could have been there. So if nothing exited at all, then that's possibly how much would be in the reactor. However, we know that we did lose some fluid elements due to flow, but we've got E of theta, and we know how to measure that, right? We established the trace experiment, and that can give us E of theta. So we could simply integrate this, and that would tell us the fraction of fluid elements that exited the reactor. So that fraction times that flow, that tells us how much has exited the reactor. And then, of course, we have to multiply this by delta theta because that's a fraction, but we need to multiply by the number of fluid elements that exited also. So then if you rewrite this as, Q delta theta times 1 minus integral naught to theta E of theta, that's equal to V I of theta delta theta. And you can see the relationship now. You can see I of theta is then simply, you can divide V delta theta. So Q over V is 1 over tau. So this is 1 over tau. And then the delta thetas can cancel, leaving us with simply 1 minus the integral naught to theta E of theta. And that's the other half of it, right? We know how to get E of theta quite easily. E of theta is simply the concentration of tracer, the function that you get, divided by the area under that function. And in fact, I should say here theta instead of t. So you just integrate under this function. So that gives you E of theta. So E of theta is some function. So it's something, whatever it is. And then we can stick that same function in here and we can get I of theta. So that's everything fully developed for us now. We've defined some variables, t, t naught, and theta, and we've introduced some distribution functions, I of theta and E of theta. And we understand what all these are, and now we know how to estimate all these. And of course, we'll do lots of practical examples on how exactly to do that.